Homework. Right, stress concentrations. That was the last thing we did, believe it or not. Since we didn't have Tuesday, we go back to last Thursday. We did stress concentrations. We did, I think you uploaded them. Some of you did at least.
Oh, I did not.
So if you didn't, make sure you get it to me, but we did 17 and 18.
Yes.
Get those two,
Huh?
get those two, 17.
If you didn't upload them,
Oh, right.
leave them with me today, type of thing. If you uploaded them, then you're good.
Yeah, I did, and I have to.
But were there any questions?
Yeah.
Or were you good? Both of them? Want to work your way through them? I'm an easy target today, so I'm okay with that. Yeah?
I got different answers than the book.
Ooh,
Let's put it that way.
well, that's not usually what we want. Long flat steel bar, 13 millimeters thick, 120 millimeters wide, semicircular grooves. Tensile load of 50 kN, determine the maximum stress in the plate. So going straight after this equation. Stress max equals what? K P over what? Area net. What is a net?
Area left after the whole.
Yep, so it's this area right across here. If I draw it kind of three-dimensionally, it looks like this. Where it's 13 millimeters thick. And then whatever this reduced area is, in the first case, the radius is 8. So that's the radius and that's the radius. So it's 16 less than 120, right? So for the 8, it's going to be area net for the 8 radius is going to be 13 millimeters times 16 less than the 120, right? Because we have 8 here and 8 here. So that would be what? 104? Is that right?
Yes.
Yeah, all right. So then we need this K factor thing. So we got area net, that's this. We know P, right? That's 50 kilonewtons. So we need K. How do we get K?
Yeah, R over D.
Yep, you do R over D, and you may need to look at the graph to see, like, make sure you understand what everything is, right? For the semicircular grooves. D is this distance that's left over, right? And R is R, that's the radius. Okay. So in the first case, it is 8 over D, which is what? 104. That number is, hang on. Let me finish one thought here, 0.076, is that right?
Yeah.
All right, what?
That's what I did wrong. Because the book kind of specified the time that rated by 2 because it's on both sides.
It's showing the diameter though, right? So this shows the diameter as 2R. Yeah.
That's what I got confused.
Yeah. I don't know why they do that. Why don't they just say R is radius?
Exactly.
Why make it confusing?
And
I
that-
did
that's
that
what,
initially and I got. the
Yeah,
wrong
it's a
answer.
little, I agree, it's a little weird that
That's
they
what I
show
got
it like that.
confused.
So it's 2R, so R is R, the radius. It's like, why didn't you just say it? And it's the same way here, right? Actually, they show it as a radius though, a little more clear.
yeah, so that one, yeah.
Yeah, so that would throw your R to D ratio off. You're right.
Yep.
All right, so a 0.076. Semicircular grooves, all right? And again, we're reading a graph. 0.076, this is 0.1. Agreed? So this is 0.05 at that line. So halfway between is going to be like 0.07, about as good as you can get. So I would just go halfway up, find your semicircular grooves to right here. And then come across, it's somewhere between 2.4 and 2.6. Pretty close to halfway, I would say. So I'd probably just go with 2.5. But you're gonna interpret that all a little different, and I'm okay with that. Like if you're getting 1 point something, then you're way off. That makes sense? What numbers did you get if you did it, or if you remember?
2.45 for
Yeah.
the actual,
I got 2.5, so, okay, that's all good. It's perfect, but that'll make your answer different, right? So to match the book, you'd have to use the same exact K factor that they used, and you don't know what they used, so. I mean, you could probably reverse engineer it to figure out the K factor, but no need to do that. All right, so now we have everything we need for this 8, right? For the radius equaling 8. I'm gonna use my 2.5. I'm gonna use my 50 kilonewtons. And the net is gonna be the 13 millimeters and 104 millimeters.
If the book used 2.4 instead of 2.5.
Yeah. What's the book get for an answer on this one?
88 point something, I can't remember exactly.
Oh, wow, I just screwed that up, okay. I can't multitask, sorry. You're gonna just focus here. So I get 0.0924, and what are my units? Yeah, so that's a kilonewton millimeter squared. And what is a Pascal?
Yeah, I was going to tell you that.
Newton meter squared. So if I want to get it to pascals, I got to get my kilonewtons to newtons.
That's what I did.
Good. And then you got to get your millimeters to meters. And then you'll be in pascals. Okay, I'm guessing that's going to end up to be a factor of 3. And I'm going to end up with 92.4. But what the book get?
88.8.
Yeah. So
I got-
I'm off because I used a different K value than the book.
I got 0.089.
Oh, so you were right on it with your, and you used what as a K factor? 2.41. Okay. Perfect,
Pascal's 88.76.
perfect.
Got 89.
So what's interesting, and a student found this last year. Online, you can get the tabular information for this thing. Yeah, and you can literally put in your R to D ratio as 0.076 and semicircular grooves, and it'll give you the exact tabular number for the K factor. I was like, oh, that's pretty cool. I probably still have that website, but not that necessarily for us. Like in analysis, you're gonna look at that stress and you're gonna say, is that anywhere near failure? If it is, factors of safety are gonna just take you out, right, of even making any kind of decision of whether it's close or not. So did they give us the material on this?
steel bar, but not.
A steel
not
bar?
that kind of steel.
Yeah, so if we just look up generic steel, anyone remember the yield for generic steel in the metric system? It's 250. So those are pretty good, not to memorize, but you just will, if you think about it enough, you'll just, these numbers for mild steel, which is a super common material. You'll start to just remember what they are. For the metric, mild steel, 250 for the yield. It's not KSI, my book says KSI, it's megapascals in the metric system. So if yours says that, that's an error, it needs to be MPa. So 250 MPa, and we're coming up with 92. I'm coming up with 92.4, you're getting 88. Well under the yield. no problem, right? Factors under the yield, we can even figure out the factor of safety, it's like a 2 point something. But not a problem. Same exact process for the 21 and the 38. What'd you get for the stress, maximum stress with the 21? Anybody? Or what the book get?
I'm working on that.
21, the radius of 21.
Oh.
So what changes? Well, area net changes. And the R to D ratio changes and the K changes.
Oh, yeah.
So a lot of things change.
1 divided by 7.
What'd you get for the stress max?
Oh, like
How much?
91.20.
90.8. So it went up a little.
91.
Okay.
That was lower than
These are all just different K factors. What'd you get?
91.
Okay. And then what about for the 38?
111.
110.14.
Okay. Good. All of those are good, right? That just means we're reading that K factor different. It's fine. All well under the 250 too. So that's a lot of material to remove. It's a lot. But 50 kilonewtons is not a huge load on something that's 13 millimeters thick. So 25 millimeters is approximately an inch. So we're talking a 1/2 inch steel bar. It's pretty thick. Right? So we do have to think about those things though, like what's gonna happen to the structural piece? Are we gonna pop holes in it? Like, it just adds a complexity to thinking about the stress levels. Cool. Good. Questions? It was a hot minute ago that we did this, so. Yeah. Happens. I forgot. Like, what did we do last? I had to look. All right, this is the second one, which was, I think, 18. Is that right?
So it's okay if in the book we just delete or erase the two on the scale for the scale. Page,
On the table?
On the table, yeah.
Yeah, some people's book is correct.
Yeah,
Mine is not, mine is not.
Yeah, mine says.
Mine says KSI for the SI units.
No, I'm talking about for the scale. That it indicates two times radio. It should be radio only.
Oh, no, that's, their diagram is correct, Jorge.
No, but I'm talking for the group systems. You see, it said times 2,
2R.
2R.
That is correct, because it's showing you the diameter. Look at what it's showing you, the arrows.
Yeah,
So it's showing you the diameter.
Oh,
So
okay.
it's saying
But
this
in reality-
distance is 2 times R.
Okay, but reality.
Reality is R, it's the radius.
So my mistake was that I was radius times 2.
It was just, I fully agree, it's confusing the way they have it, so. It's not radius times 2, it's just the radius.
Just a radius.
Yeah.
Yeah, that's what I was.
Yeah, and for this one too, it's just the radius. All right, so this one. 18, yeah. 18 says long flat steel bar, steel again, 4 inches wide. Yep, 3/8 inch thick, yep. Reduced to 3 inches, so pretty big reduction. There's circular fillets of a 1/2 inch on each side. Axial load of 12,000 pounds. They want to know the average stress in the 4 inch here. They want to know the average stress in the 3 inch here. And then they want to know the max at this transition. Okay, so this will be interesting. The 4 inch, if we want to know average stress, that's just P over A. So that's going to be 12,000 pounds over 4 times 0.375. That's 3/8 of an inch. Anybody have that number?
It's
1.5?
1.5.
1.5 what?
No, that's like.
Oh,
that's
no.
I was like,
It's 8,000.
8,000.
there's a lot of you agreeing to this. I'm like, I don't think so, but I have a scattered brain. 8,000?
Yes, sir.
PSI, pounds per inch squared. And what, did they give us an allowable for this thing? They did not, but they said it's steel, and we know steel is 36,000 for the yield. So this average stress, 8,000 pounds, 8,000 PSI. So that's clearly no problem. Let's do the other average stress, which is gonna be 12,000 divided by 3 times 0.375. And that stress is 10,666 PSI. Again, well under the 36, so we're good there. All right, now let's do the stress max. So that is, just to reinforce this, K P over area net. We get K from the R to D ratio. What is R?
0.5.
R is 0.5. What is D? 3. What is the R to D ratio? 0.17. Yeah? Agreed?
Well, wait, I think it would be 1.
All right, so it's D is 3 for sure. And R is 0.5, so this is good. 0.5
Yeah.
divided by 3.
I got 1.6 would be.
I do too. It's not 1.7.
Yeah, but you just.
It is
Well,
round,
you're
it
right.
is rounded. Okay, okay,
Yeah,
okay.
what I do is I just put a slash on top of the 6 and make that it continue.
That's a good idea. I like that.
Sick.
All right. 0.166. So here is 0.1.
Oh,
Here is 0.15. Agreed? So 0.16 is like right there. Yeah. And then we have, what is our shape?
1.7.
Fillets. So we come up to here. That's where I'm at. And I say it's above 1.7. That would be halfway. It's barely above 1.72. I don't know where I'm getting that.
I just said the numbers.
So K is for me 1.72. Yeah. So we need area net. And what is that? Yeah, so the area net is gonna be that reduction, right? It's gonna be 3 times 3/8. Yep. 3 inches times 3/8 of an inch. What that is. 1.125 inches squared. So now we have it all for this equation. We've got K, I'm using 1.72. That's a pretty big factor, right? That's a straight multiplier to stress. Just straight on multiplier. 12,000 for P. And area net 1.125. $18,346.
Yeah.
Something in that range, right? PSI. So. In the 4-inch, 8,000. In the 3-inch, 10,000. But at this transition where it's going from this larger shape to the smaller shape, the stresses are massively increased. 18,000 is huge over 10,000, right? If we're still comparing to the yield at 36, we're fine, but you know, factor of safety is going down like the 2, right? If the factor of safety, some experts said, hey, this can only go to 20,000, then we're getting super close. So we always have to calculate these stress risers. Excellent. Nice job. Questions? School? It's not too bad. Easy peasy. Easier than combined materials, which is what we're gonna do now. Just keep on with these stress considerations. Yep, if you didn't upload it, turn it in.
Turned in the quiz.
Hmm?
Do you know if I turned in the quiz? Because I have it done. And I got
Like
it.
in Blackboard or email. Some came to
Either.
me via email, some came to me Blackboard.
Do you know if I submitted it?
I
Because,
don't, off the top of my head.
okay, I can check.
For
But,
some reason, I thought you did.
okay. I have it done. in
I
case I
agree.
didn't.
The one where you said,
I
actually,
think it's so tan.
I lay out in
Like
the sun.
freaking playing softball,
But-
I lay out in the sun.
Yeah.
Seriously?
Yeah.
Was it the 2 for metals?
I'm gonna be an old lady
Yes,
someday.
yes, it was.
Alright, what was
Well,
your question?
but the one
Yeah.
quiz where you said, oh, it's due the next
Yeah,
day.
yeah, yeah.
It's
Okay,
the-
wait, that's a great
Yeah,
day, right?
yeah.
Okay. that's fine.
Was
I
it,
just-
number 9?
Oh, I have
chapter
products.
9, number
As long as
7?
you don't see a 0.
Oh, I forgot the
What's it
progress
called?
report page.
No, wrong quiz.
Okay, thanks.
All right,
Wrong quiz.
so let's go down memory lane, because that's always a good thing to do. If I gave you a concrete column. Oh, I can't use a circle, that's just not gonna look good. So we're building structural columns here. And this is a 6-inch diameter concrete. High strength. Because there's 2 concretes in the book. There's high strength and low strength, or average strength. How much, with a factor of safety of 3, how much load can we put on? So I'll give you a second to capture that. How much load? So P stands for load, like if we're doing stress, it's P over A. P stands for load, and load has what unit? Pounds. Yep. So that's always a good thing to think about. Like if it says how much load, how much P, really they want to know how many pounds. So it's good to write it like, you know, that's what we want to know is pounds. If it said like how much stress is on it, then it would be pounds per square inch or PSI, right? So in this case, you know the geometry, so you know area. Right? And you know the stress equation is P over A. And P is what we want to know, right? Load. So if we know area, and if we know the material, then we can look up the properties of the material, right? Yes, sir.
Which concrete again?
High strength.
It just doesn't,
We're sticking with it, man.
it just says concrete.
I know. One's stronger than the other, though, you gotta admit. Yep. So the other piece that you're given is this factor of safety thing. What the heck are we gonna do with that? Is? Yeah, we're gonna look up the property of concrete. That's gonna be this. We're gonna put a material property in for the stress. Right? And what is the stress allowable for high strength? Yeah, the only thing you're given is the ultimate strength, 4,000 PSI or 4 KSI, right? So we could put the 4,000 in here. I'm gonna put it in pounds per inch squared. Right, but that's all the way up to it exploding. That's the ultimate strength. What do we do with this? We should take the stress and divide it by the factor of safety. That brings it down to a comfortable position for the designer or the builder or somebody who has said needs to have a factor of safety of 3. So we apply the factor of safety to the stress. That's important because anybody looking at this will want to see the real load. Like, what's the real? We don't want to apply the factor of safety to the load. We want to apply it to the stress. And it's good to kind of show it like that. Like, hey, I looked up the material property and then I divided by the factor of safety. And that became my stress limit. Right? And everyone knows I'm using high strength concrete. That's this 4,000, factor safety of 3. I'd like to know P. I don't know it. And then I can put the area in. What's the area? Either pi r squared or pi d squared over 4, whichever one you want to use. So I'm going to use pi 6 inches squared over 4. That's going to be my area. High strength concrete, this much of it, how much, do you think it's gonna hold a lot? A little, what do you think? Concrete strong or not so strong? Concrete's pretty strong. Let's see what it holds. You guys get that? That's a lot, folks. It's like, what? I don't know, 15 of your cars.
What's the ultimate strength?
What's the what?
The ultimate?
So we used this stress. And that's the ultimate stress, because that's the only thing we're given for concrete. Right? That's why we used it. So is this even close to blowing up the concrete? No, because we took that number, 4,000, and we divided by 3. So this is 3 times safe. Does that make sense? All right, let's do it again, one more time. This time the geometry is a steel pipe, a hollow steel pipe with the ID inside diameter of 6 inches and the OD outside diameter of 6.25 inches. And it's hollow.
Wait, the 47,000 says 3 times safe, what?
Yeah, so we took 4,000 divided by 3,
Yeah,
and then we did this and multiplied this across and got that number.
no, I gotta get the number, but.
Okay, so we took the 4,000, which is the blow up stress, and divided by 3.
That's.
So we are 3 times under 4,000
Oh.
for the stress. Then we took the area, multiplied it across and got this load, right? So the concrete, how much would it take to blow it up, like destroy it?
You'd have to,
3 times. this
So you'd
number,
have to just leave it. if
over
you
100,000 pounds to blow it up.
So if you just have the 4,000, you didn't divide it by 3, then you can find out the.
You can find out the rupture load, yeah,
Okay.
yep. But we don't normally work anywhere near that rupture load, right? We don't wanna play with that. We don't want anything blowing up. So that's why we apply these factors of safety, huh?
It's fun though.
Yeah, it is, sometimes, depending on if you're driving across it or not, when it blows up. Or flying in it when it falls apart. It's not so fun, I'm sure. No, all right, so how much load? How much heat? Same process, right? And we'll use a factor of safety of 3. Again,
And it's the same.
mild steel. So what's the yield stress for mild steel?
36.
36, you were close. 36,000. And what are we gonna do to that number?
divided by 3.
Yep. PSI, we're gonna divide by 3 and we're gonna set it equal to load over area. So we have to be able to calculate the area. And it's the area of the steel that will carry it.
You have to take the area of both and subtract them.
Yep, so you gotta take the outside area, which I'm gonna use pi 6 squared over 4 and subtract the inside area. Oops. Outside area is 25. Right, 6.25 squared. And subtract the inside area, pi 6 squared over 4. You gotta take one area, subtract the other area to get the area of the steel. Eight, 6, 3. Anybody else get that?
Yeah.
Cool. We gotta know the material to calculate load. We gotta know the area, right? Once we have that, factor of safety, if it's there, we apply it. We can come up with these loads.
What
Good?
is the load on directly vertical?
Yeah, so it's a directly vertical, that's a good question. It's a directly vertical load. And it's gotta, like, it would need to have a plate, right? Cause it's gotta hit the whole surface area. And then that load would be coming straight down and it's symmetrically loading that. That's the assumption we're making. We will do asymmetrical loads, which is really a pain, because that stresses one portion more than the other. It's brutal. But we're not there yet. We're just doing these perfect loads. Same with this one. It had to have some beam that covered the whole thing. And then that load is just perfectly distributed on that surface, okay? So the next step is to do this, is to say, okay, here's my pipe, same pipe, and now I fill it with concrete. So I have my mild steel out here, and my concrete in the middle, which is 6-inch diameter. And then this outer thing is 6.25-inch diameter. This is steel. And that is concrete. And this is called combining materials, or a combined material stress. How much will it take? How much load? It's not just adding the two together, like, because now these things are acting together. They're helping each other. But one is a much lower strength material, the concrete. One is a much higher strength material, the steel. But the steel is a much smaller area, and the concrete is a much greater area. So we have to have like formulas and strategies for combined materials. There's only one that we do in this book, and it's by far the most common. And that's the condition of a column, essentially, where the top is loaded, perfectly loaded, the whole thing is loaded. So not just part of the concrete and part of the steel, but we have a plate or a cap, and it goes over the column, and then we load it. And what's important about that is when it changes in length, because when we put these massive loads on it, it's going to deform, right? The change in the concrete is equal to the change in the steel. In other words, the elongation has got to be the same, right? When it squishes the same amount. When that happens, we can then set those two formulas equal to each other. That's the formula magic of it. I don't really need you to fully digest the formula magic, but no, I don't. But some folks like to know where these formulas come from. And I don't blame you. Like, you're supposed to just believe them. But they derive it here. In the combined material section, they start with this concept that we just mentioned. That the elongation of one material is equal to the elongation of the other material. Right? If it's going to squish, they're going to squish together. Everyone agree with that? Yep. So then anytime you have original length and then change, you have strain. So then they said, oh, the two strains are equal to each other also. Well, that's obvious. If you think about the formulas, right? Original length was the same. And now the deformation is the same. So the strain's the same. So then they just keep boiling down the equation and they say, oh, well then, if that's true, then this is true here. It's kind of weird that they go here and then here. Strain is equal to stress over Young's modulus. Again, this is how they derive the equation. So they say, oh, these two are the same, and so these two are the same. So then we know this is true. So now this is true, right? So they just keep working. This is what honestly mathematicians do. Or if you're wondering what masters in engineering would do for you, it's this kind of thing. Thinking through, like, if it changes and the strains are the same, if the strains are the same, then we can extrapolate that into the stresses being of equal to their moduluses, and then boom, they're walking through the whole thing until they get to here. And that's the one I really care that you care about, right? But if you want to know where it came from, the book does a pretty good walking through of it to see how they're deriving this equation. So this is load on a combined material column, basically. So it says the stress in B is the lower strength material. A is the higher strength modulus. So if you have a higher modulus and a lower modulus, you're gonna name the higher modulus steel, in our case, material A. Material B is the weaker one. All right? Material B is here, the stress in B. N is what we call the modular ratio. That is EA over EB. So that you just look these up. When you're given combined material of steel and concrete, you look up E for steel, it's material A. You look up E for concrete, it's material B, and you figure out the modular ratio. It's gonna be like 2 or 1.7 or something like that. That's what this is. The modular ratio of this combined material problem. Okay? Area A, that's easy. That's the area of the steel. Area B, that's easy. It's the area of the concrete. Okay? The stress in B, the weaker material, which is concrete, gets put in here. So this would be, if we don't have any factor of safety, it would be our 4,000. If we have a factor of safety, we take the 4,000 divided by 3, and we put it in here. So the formula is telling you the weaker material is going to rise to its maximum stress. The stronger material will be some portion under that stress. You're not going to stress out both the materials equally, right? Steel is going to be like, oh, I'm feeling some load. Concrete's going to be going like, oh, I got the entire load, as much as I can take, right? So we allow the stress in B to rise to its limit. That's what we put it in, stress in B. And then we don't even put in the stress in A, because the modular ratio is handling that for us. So combined materials run this equation. So for our problem, it would be stress of the concrete, like if we can calculate it real quick. So P is going to be stress in the concrete. We'll use our 4,000 PSI over 3. There's a couple other ways to do this, but we'll just go straight with that. N is going to be the modular ratio. So N is going to be EA over EB. So the modulus of elasticity for steel is, you can look it up. $30,000 KSI, yep. So it's 30 million, 30 e to the 6 PSI. So as long as you keep the units the same, you'll be fine. So I'm going to use PSI, so it's 30 e to the 6. And then what's concrete?
0.50.
In PSI. How much? 3,600. 3605 KSI, so 3.6, right, PSI. So if you're gonna do, if you do KSI, you can do 30,000. That might be easier. 30,000 KSI over 3605, right? Both of them in KSI. Yeah. Agreed?
I'm gonna change it later.
It doesn't matter. This is just coming up with a unitless number, right? You just want this unit to match this unit. So I'll leave them both in KSI. 30,000 KSI, 3,605. What's that N value? Correct. N equals, yeah, if you want, but you have to do them both, right? So you don't have to do that. 8.3
Would it matter if you multiply them by 1,000 because you're
No.
multiplying them?
Yeah, wouldn't matter at all. You could actually use 3 and 3.6,
But same.
right? Or 30 and 3.6. So it's just as long as the units are the same, you're fine in the modular ratio. All right, so there's my modular ratio. What's the rest of this formula? Gotta find it again now.
Area A. plus area-
It's on page, 228.
Yeah, I'm just using it right out of the back in the chapter somewhere. So it's that modular ratio 8.
Times
Yep, 8.321 times area of A, which we already know, we calculated that once, but we can write it again. Area A is, this is the area of the steel. Oh, I'm just gonna look it up. Because we already did this once. Area of the steel was 2.405. I wrote it down right here because I knew where I was going with it. 2.405. So that's area A. This is the modular ratio N. And we're gonna add to it area B, which is pi 6 squared over 4.
That also get multiplied by-
Huh?
Does that also get multiplied by that?
No, not in the formula. No, no, no. So the formula is stress in B. Let's write it out so we can see it. N times area A, that's N, plus area B. That's the formula. Yep. Anybody get a number?
$4,381.
Anybody else? Hmm? Yeah, I'm gonna redo it too.
Okay, that's what I'm getting.
Yeah, is that what you're getting?
We'll do it separately.
Yeah. So the concrete by itself. 37,000. The steel by itself, 28,000. The combined. Working together, these two materials, 64. So it's not doubling like the concrete, right? It's not doubling this. It's this ratio. This modular ratio that actually controls it, how the two materials, their elasticities work together. So. It's tough to figure out like what that load is. Yep. Questions? Huh? What? Talk to me.
Is there homework Tuesday?
There is a homework, it's number,
Chapter 11.
yeah, oh yeah. I don't remember the number, I'm looking for it though. So 53, 52. It's 51. 1151.
Chapter 11, number 51.
I was gonna give you 52, but 52 is ripping
It's just
hard.
one
It's a
problem.
good thing, yeah, just one's enough.
Are you gonna give us, Tuesday's homework with today's homework combined or?
Or is there no Tuesday home? We didn't have class.
I just omitted it. We're just picking up